All right, if you're a life sciences student prepping for the Lebanese Baccalaureate, you're in exactly the right place. We're going to build your essential math toolkit, and I promise, it's not just to solve problems, but to totally change the way you see the connection between math and biology. So I want to kick things off with a question that I know is going to sound a little weird at first. What could possibly connect the way your body fights off a virus with the way electricity flows through a circuit? I mean, they seem like they're from completely different worlds, right? Well, the answer is mathematics. It's the hidden language that describes the patterns and principles in both of them. And get this idea isn't some secret. It's right there in the preface of your official math textbook. It calls mathematics an interdisciplinary science. And that right there is the key to everything. Okay, so let's get one thing straight right from the start. Math isn't just another subject you have to memorize. It's the universal language, the code that allows us to describe, model, and predict the world you study in physics, in chemistry, and especially in life sciences. Just think about your exams for a second. The questions aren't isolated in these neat little boxes, are they? No way. They're designed to make you connect ideas across all these subjects, to analyze data, to interpret graphs, and to understand the numbers that really govern everything from population growth to chemical reactions. So how do we actually start speaking this language? Well, the first and honestly the most important tool in our toolkit is the function. Now, I really want you to stop thinking of functions as just these boring, abstract equations. We're going to see them for what they really are, models that tell a story. Look, at the end of the day, a function is just a simple rule that connects an input to an output. But when we put it on a graph, whoa! That's when the magic happens. It becomes a visual narrative. It tells a dynamic story of how one thing changes in relation to another. And usually that means how something changes over time. And this is the perfect example. Just look at these two graphs side by side. On the left, from your life sciences book, we have the story of an HIV infection. The virus level shoots up, the immune system fights back, T-cell counts drop. On the right, from your physics book, it's the story of forced oscillations. Totally different situations, right? But do you see it, that mathematical story, that shape? It's the exact same fundamental pattern. And that is the power of functions. They let us take a messy, complex reality, simplify it, but in a really rigorous way, and tell its story so that we can actually read and analyze it. This is exactly what your textbook means when it talks about being simplified but rigorous. Okay, so if the function is the story, then we need a tool to find the action, right? The most dramatic moments. And that brings us to tool number 2, the derivative. I mean, how do we find that exact moment when things are changing the fastest, or when they stop changing completely? How do we quantify the real turning points in the story? Well, that's exactly what the derivative does. It measures the instantaneous rate of change. Now, I know that sounds super technical, but visually, it is so simple. The derivative is just the steepness, the slope, of the graph at any single point you decide to pick. Let's jump back to our HIV graph. See how the curve isn't a straight line? Its steepness is always changing. The first derivative tells us the exact moment the T-cell count is dropping the fastest. But we can go even deeper. The second derivative, that tells us about the acceleration of that change. Is that drop in T-cells speeding up, or is it slowing down? And that, my friends, is the difference between a full-blown crisis and a condition that's becoming manageable. Okay, this all sounds great in theory, but the real question is, how does this actually help you on your exam? Let's put this toolkit to work right now. Okay, here it is, your 3-step toolkit for crushing any graph they throw at you. It's super simple. Identify, describe, and analyze. First, you identify what the axes are even talking about. Second, you describe the overall shape. What's the plot of the story? And third, you analyze the rate of change, the slope, to find those critical moments. Where is it steepest? Where is it flat? And how is that steepness itself changing? Let's try this out right now. Here's the classic graph from your life sciences textbook showing antibody levels in an infant's blood. Let's use the toolkit. Okay, step 1, identify. The y-axis is the amount of antibodies, x-axis is time. So the story is about immunity over time. Easy. Step 2, describe. You see the pink line? Those are the maternal antibodies and they're falling. The blue line? That's the infant's own antibodies. It starts at nothing, goes up, and then kind of levels off. Got it. Now for the fun part, step 3, analyze. The infant's antibody production rate, that's the slope, remember, is fastest where that blue curve is steepest. But hang on, look even closer. See right around here? The curve changes from bending up, what we call concave up, to bending down, or concave down. That one specific spot, the point of inflection, that's where the rate of making antibodies hits its absolute maximum. That's a huge insight, and you only get it by thinking about the second derivative. So you see, this way of thinking, seeing functions as stories and derivatives as how we analyze the action, this is your essential toolkit. This is what ties all the sciences together. So what you're looking at here, this is the math that actually writes these stories. These are called differential equations, and they're literally built using derivatives. They describe the rate of change itself. For instance, an equation could say that the rate a population grows is directly tied to how big it is right now. And to solve that, we use these incredibly powerful functions, like the exponential function, e to the x, for things like growth, or its inverse, the Neperian logarithm, ln of x, for stuff that scales differently. Think measuring pH or the Richter scale for earthquakes. It's just mind-blowing that the same mathematical ideas can model everything from electrical circuits to radioactive decay. So really, it all comes down to a choice. Without this toolkit, you're just stuck memorizing shapes, guessing what they mean, and thinking of biology and physics as totally separate things. But with the toolkit, well, now you start to understand the why behind it all. You can do precise analysis, and you start seeing these amazing universal principles that connect everything in science. And that, right there, is the real takeaway. This is so much bigger than just passing an exam. This is about learning to think like a scientist or a doctor or an engineer. It's about wielding this powerful language to see and understand the world on a much, much deeper level. So, I'll leave you with this one last thought. Now that you have this toolkit, this whole new way of seeing things, what other stories can you start to read in the world around you? In the news, in data, even in the patterns of your own life? Because the language is there, just waiting for you to understand it.